The following program is a special presentation of the Big Ten Network, produced in association with the University of Iowa.
March 2nd, 1972, the Pioneer 10 spacecraft leaves Earth for mankind's first flight to Jupiter. On board are 11 scientific instruments and one plaque. Within 2 years, the spacecraft flies by Jupiter and acquires enough energy to propel itself on a continuing odyssey of discovery, seeking the boundary of our solar system. And as an emissary from Earth, the 6 by 9 inch gold plaque tells any finder, even millions of years from now, that our planet evolved an intelligent species capable of thinking beyond its own time and beyond its own solar system. Today, Pioneer 10 is nearing that boundary, but now there's only one functioning scientific instrument. It's the Geiger tube telescope of James Van Allen, sending data back to him about the mysteries of space from billions of miles away. At the dawn of the space age, he was there, vital to the success of America's entry into a new era of discovery. His early investigations of cosmic radiation in Earth's upper atmosphere with simple rockets anticipated America's entry into space. And he was ready in 1958 when the U.S. officially entered the space age with Explorer 1. In the following years, he was central to America's space missions, which made new discoveries that began to unravel the mysteries of the planets and outer space. Today, he continues to explore, still receiving and analyzing data from Pioneer 10 as it ventures to the edge of our solar system and then beyond on a seemingly perpetual flight of discovery. James Van Allen grew up in the small Iowa town of Mount Pleasant during the 1920s. He was an exceptional student, became class valedictorian, and exhibited an intense vision that even then looked beyond our planet.
So I was more interested in really comprehension, understanding, for example, why do planets orbit around the sun? A great classical puzzle. And when I began to get that through my head, I was delighted, to understand the physical principles of that.
Together, Don and Jim attended the local Iowa Wesleyan College, where Van Allen was introduced to physics and practical hands-on research methods by Professor Tom Poulter.
My advising professor, Tom Poulter, was a great inspiration to me. He was my college physics professor and was later the chief scientist on the Byrd expedition in 1933-35. Tremendous individual, a brilliant guy, and one of the most ingenious people I've ever known in my life.
Van Allen was assigned the task of testing and checking the magnetometer, a device that measured magnetic fields which Poulter would take with him to the South Pole. Van Allen decided the best way to learn was by doing, so he used the instrument to conduct the first magnetic survey of his local county.
So these kind of things taken together sort of led me to realize that there was such a science as geophysics and astronomy were real sciences in which ordinary human beings like myself could participate and do original things.
Following the family tradition, Van Allen pursued graduate studies at the University of Iowa in Iowa City, completing a master's degree in 1936 and 3 years later a PhD in the new field of experimental nuclear physics. With the onset of World War II, most of America's physicists were mobilized to support the war effort. At the Applied Physics Laboratory, Dr. Van Allen worked on the VT, or proximity fuse. He helped develop the miniature radio transmitters that were placed on top of Navy anti-aircraft shells. The transmitters would detect nearby aircraft, ignite the fuse, and explode the shell, significantly improving the effectiveness of shots fired at attacking Japanese planes, thus saving thousands of American lives. Lieutenant Van Allen served in the Navy for 3.5 years, mainly in the South Pacific Fleet.
My most important part of it was development of a vacuum tube, so-called rugged vacuum tube, which was obviously essential to the fuse. That was long before the days of transistors. rockets. In fact, there was something like 80 million of these rugged vacuum tubes incorporated in my design made during World War II.
When the war ended, the U.S. Army quickly seized many German V-2 rocket parts. They were brought, along with Werner von Braun and a few members of his rocket team, to the United States to advance rocket development here.
I was among the fortunate ones who were selected to come with him. There were about 127 of the old Peenemünde group that came to this country.
And they quartered the engineers under something equivalent to house arrest at Fort Bliss near White Sands Proving Ground. And they brought the rocket parts to White Sands Proving Ground. The idea being to check them out, to reassemble them, learn how to work with them, and make a number of firings for general assessment and experience in handling large rockets.
In early 1946, the Applied Physics Lab formed a high-altitude research group led by Dr. Van Allen. He coordinated construction of instrument packages placed in rocket nose cones for exploring cosmic rays and ozone in the upper atmosphere. Early V-2 flights also produced the very first high-altitude, large-area photographs of the Earth.
A group of us called the V-2 Rocket Panel comprised about 8 or 9 people, such as myself, who were interested in doing high-altitude work. And we allocated the flights in a sort of equitable manner among the various groups on an entirely informal level without any paperwork, whatever.
I was particularly happy to meet him because I had known his name for several years as a cosmic ray researcher.
There's still a certain amount of uneasiness in the United States about having a group of former enemies conducting rocket experiments here. But I found very soon that one in particular was Dr. Stuhlinger, who was a physicist, a member of this group, and he and I struck it off very well together right away.
I had the feeling that we could talk really like scientist to scientist, that we were not bothered by any political considerations. We talked about our common interest in research and in finding out how this world is built and how it works. And that was a common ground which united us and joined us for I would say for the rest of our lives.
In 1948, Van Allen authored a report that attracted media attention. The New York Times ridiculed his conclusion. Time magazine questioned his prediction that in the future, satellite missiles would be used to collect scientific data above Earth's atmosphere. Once again, Dr. Van Allen's vision was ahead of its time.
We were just eager to have greater capabilities in those days, and we realized the immense potential if we could just get away from the Earth and outside of the Earth's atmosphere and make measurements where they'd never been made before and settle various basic questions.
Eventually, the captured V-2s were expended, and in the summer of 1950, North Korean armed forces invaded South Korea. With superpower ideologies clashing, military funding for scientific research began to decline. Dr. Van Allen left the Applied Physics Lab, accepting a position at the University of Iowa, where he had received his master's and PhD degrees. As a professor and the new head of the university's small physics department, his life took a welcome return to academia.
But I began to look around for something in which I'd have more freedom of choice. And that's when I was fortunate enough to get an offer from the University of Iowa to come back to my alma mater as a professor here. I've, of course, always enjoyed teaching. Teaching has been a very important part of my life.
I'm not sure he chose us or we chose him, but he was adept at giving us as much responsibility as we could handle, and sometimes more than we could handle, and sometimes we fell on our face.
Van Allen has always relied heavily on graduate students to take the lead, take the initiative in doing a project.
In retrospect, he treated us amazingly like colleagues. Completely respected anything we said, although I'm sure a lot of it was absurd.
At Iowa, there were no university funds to continue his research, so beginning in 1951, with a group of eager graduate students and surplus weather balloons, Dr. Van Allen resumed his investigations of Earth's upper atmosphere.
Well, now, is this similar to the kinds of rockets, these guided missiles that the military have been using?
They have some of the same elements to them. However, theirs are completely unguided missiles. We carry them up in a balloon to about 70 or 80,000 feet, then launch them from there.
Well, I guess this is the device I heard that you more or less invented. What do you call that thing?
Well, we call it a rockoon, a combination of a rocket and a balloon.
And it first goes up in a balloon, and then from there, up in the air, it's automatically shot off to go higher. Is that the idea?
Correct. Yes, with a very inexpensive rocket now, we can get above 60 miles altitude.
He had developed a supply of components that were used for building electronics. Much of this came from military surplus. He operated with an extremely austere budget. Support in that period, I believe, came mostly from the Office of Naval Research.
So you might say that we hitched a ride to launch our rockoons on the Navy ships as they were going about their appointed rounds, and took advantage of that way to get the rockets where we needed to get them.
Following World War II, a series of international events unfolded that contributed to the Cold War. In 1948, the Soviets blockaded the German city of West Berlin. The U.S. responded by airlifting supplies into the beleaguered city. Anxiety increased when the Soviets exploded their first atomic bomb. Then, 8 months later, democracy and communism came into direct conflict in the Korean Peninsula. At the end of World War II, the Soviets had also seized German V-2 rockets. They test-launched them with the intent of developing their own intercontinental ballistic missile weapons. At stake was world dominance through military strength.
And the word that they were doing that arrived in this country in the early 1950s and resulted in our having a crash program to develop ICBMs.
To spearhead development of U.S. ballistic missiles, the Defense Department turned to the Army's von Braun Group. They were now located in Huntsville, Alabama. Their previous wartime and White Sands V-2 work made them the logical choice to design an American response to the Soviet threat. The former German rocket team also had long-term plans to launch a satellite with the same military rockets they were assigned to produce.
Von Braun was convinced that he would be the first one to launch a satellite in this country. Around 1952, he asked me to look for a scientist. He said it should be an honest-to-goodness scientist who could put his first-rate scientific instrument on board of our satellite to make it useful for science. I was happy about this assignment because I knew exactly whom I would like to choose. It would be Dr. Van Allen.
During the 1950s, the United States also began a highly secret reconnaissance or spy satellite program. These satellites would be capable of taking detailed pictures and gathering electronic information on Soviet activities. They were to be launched by the same rockets used for intercontinental ballistic missiles.
Then, separate from that, there was the program to build a satellite as part of the International Geophysical Year, a program that would be run with maximum openness for the general knowledge of everybody, to increase our knowledge about the Earth. The idea being to publish everything that it learned and to cooperate with others who might also be building satellites. And we knew from early on that the Russians also had a similar plan to build a satellite for the International Geophysical Year.
The environment was the time of the Cold War, and it was something scary. It was something for a child, it seemed very scary to have to hear about bomb shelters and hiding under our desks. And I remember first hearing that my father was going to go to Russia and being so frightened by that, and asking my father, why was he going to Russia? Wasn't he scared? And I remember him explaining to me that in the scientific community, what they do, and as they take data and exchange data, somehow that transcends what is going on in the political arena. So that there was always a sense that the quest for intellectual activity was something very special. And I do remember that, so that the Cold War suddenly didn't seem very cold to me, even as a young child.
In Washington, the Stewart Committee was established to study how America should produce and launch a satellite as part of its contribution to the International Geophysical Year, or IGY as it was called. The committee reviewed all the possibilities, and eventually 2 proposals emerged. One was from the Army's Redstone Arsenal, submitted by the von Braun Group and named Orbiter. It was based on the Redstone missile that they were developing for the military. The other proposal was from the Naval Research Lab, or NRL. It was based on the as-yet undeveloped rocket named Vanguard. In a contentious 5-2 vote, the committee recommended the Vanguard, and the Navy program proceeded as the official basis for launching the IGY satellites. The von Braun Group was to continue its work only on ballistic missile weapons for the Army.
We didn't think it was a very good idea. I mean, the argument for it, or the rationale for it, as far as we were concerned, was Eisenhower's decision that he wanted to keep this thing completely out of the hands of the military, because he didn't want to interfere with the development of the ICBM, which was a legitimate argument. On the other hand, we did not think that NRL's experience with rockets was such that they could easily do this. We predicted troubles.
Dr. Van Allen was asked to head the working group on internal instrumentation, charged with recommending experiments that would be conducted with U.S. satellites during the International Geophysical Year.
We sifted through a large number of proposals and applications for instruments to be flown, and eventually sifted out 4, which first of all seemed to have important scientific objectives, and secondly had a reasonable prospect of being technically ready to go on a satellite. So those were 4 of those. The University of Iowa proposal was among those 4, but there was no relative order assigned. They were just the 4, which would, depending on their availability, would be among the first to be flown on a satellite. Meanwhile, I was in close touch with my former colleague at White Sands, Dr. Ernst Stuhlinger. He advised me on the state of development of an alternative launch vehicle by the Army Ballistic Missile Agency, which involved the Redstone missile as the first stage. And so at that point in time, it appealed to me that the sensible thing for us to do here at the University of Iowa was to design our apparatus such that it would be suitable for either a Vanguard or a Army ballistic missile a satellite system.
In September of 1956, the von Braun Group at the Army Ballistic Missile Agency, or ABMA, in Huntsville, launched the first long-range test of their Jupiter-C ballistic missile. Orders came down from the White House to render the rocket's 4th stage inactive, thereby preventing it from going into orbit. President Eisenhower feared the Soviets' reaction to a U.S. military flight over Mother Russia.
The test flight went perfectly. It assured us in Huntsville that our rocket would work all right, and as we had expected. It gave us the possibility to go to Van Allen and say, Dr. Van Allen, we have proven that we have a rocket that can put a satellite in orbit. If we had built out of that same rocket with the same propellants, same system, except for the live 4th stage, if we had built it that way, we could have put a satellite in orbit as early as 1956, a year or even longer before the Russians launched their Sputnik.
After that successful flight, von Braun hid one of the Jupiter-C rockets in a hangar, out of sight. But it was not out of mind.
We called it the missile number 29. And we all knew, even though nobody talked publicly about it, that this would be the rocket that could be transformed quickly into a satellite launcher.
But there's no one ever had any doubt, and they didn't have any, and they in their own minds, it's clear, saw this as a convenient way to bootleg a program to launch satellites.
By September 1957, Stühlinger had become more convinced the Soviets would soon launch their satellite. He repeatedly urged ABMA's commander, John Medeiros, to seek approval from Washington to launch a U.S. satellite with their Jupiter-C rocket.
You know, he said to me, you know for yourself how difficult it is to build a satellite and to launch it. You should not assume that the Russians can do it. Relax, he said to me, go back to your laboratory and do your work there, and don't worry. He said, if I should learn anything about activities in Russia about the satellite, I will immediately crank up our activities and we will still be first. Less than 1 week after my talk to Medeiros, Sputnik was in orbit. Von Braun asked me then, well, I think Medeiros owes you an apology. Did he talk to you since that? And I said, yes, he did. But all what he said was, those damn bastards.
At the Army Ballistic Missile Agency, the von Braun group was meeting with the new Secretary of Defense, Neil McElroy, when they first heard about Sputnik.
Von Braun was quite upset at this moment, and he said, we could have been in orbit a year ago. And then he turned to McElroy and said, Mr. Secretary, give me go-ahead, and we will have our satellite in orbit in 60 days.
Meanwhile, the USS Glacier was steaming to the Antarctic on an IGY-sponsored expedition with Raccoons, Van Allen, and Cahill on board.
Somewhere along the equator, we were cruising, and we got news every day through the Navy communications network. And one day, we got news that the Russians had launched a satellite. We immediately wanted to hear for ourselves.
And within a few minutes, we were already receiving on the ship's radio the signal at 20 megahertz, which had been announced by the Soviets. So this was a great thrill, of course, and this is my logbook, which I had during the Antarctic expedition, which we were then engaged. I made some detailed recordings on a brush recorder, which we had with us. And then the next day, I sort of digested this great experience and came and recorded my notebook a number of overall impressions. And of course, the first one was one really of essentially congratulations to the Soviet Union for this achievement, which I thought was a great achievement. Well, this, of course, raised in my mind the wisdom of the Stewart decision to go with the Vanguard launch system as compared to the Army system, which I'm already pretty well familiar with both of them. And I was, of course, very skeptical about the early success of the Vanguard system because of its complexity and the fact it was a very new system. I was concerned as to what might be going on in Washington as a result of the Soviet success, and what the influence on the future of our work would be because of a great milieu that this is probably creating in political circles and the desire of the U.S. to make some kind of early response. At that time, of course, I was more or less out of touch with civilization generally and had no visualization of what an enormous impact it would have on public thinking.
It took some time for the president and others who knew what all the facts were to realize the importance of the propaganda side of all of this, of the special esteem and special aura that this suddenly brought to the Soviet Union, not only in the United States, but throughout the world. Everyone agreed it's very important to somehow or other reply technically to that by launching a satellite of our own. And we studied in great detail what the plans were. The Jupiter program had a 50-50 chance of working the first time it was tried, and the Vanguard program had only a 50-50 chance of ever working.
Then obviously the question was what instrument should fly on it. And it turned out then that Van Allen's instrument, the cosmic ray experiment, was already designed so that it could be flown on the Jupiter-C, whereas none of the other instruments were.
A month after the first success, the Soviets launched Sputnik 2 with the dog Laika on board. Then, before a national television audience, the test of a Vanguard rocket ended in a humiliating inferno. Swiftly, Washington gave the go-ahead for assembling a satellite and launching it as quickly as possible. 85 days after Sputnik 1, Missile number 29 was pulled from its hangar, and when the Explorer 1 satellite was put on board, it was ready for launch. Pickering, Van Allen, and von Braun were with the Secretary of Army at the Pentagon. George Ludwig was at the Cape working with JPL to confirm the cosmic ray experiment was counting properly.
We got reports from the Cape to where the launch looked as though it was successful. And in fact, one of the JPL people down there, Al Hibbs, made a calculation of the orbit and announced that it was on such and such an orbit. On the basis of this, we could determine that it should be picked up by our California station at a certain time.
So we waited in a very tense period, all of us there, and the sort of silence sort of settled over the whole group of us, and we sort of drank coffee and sort of chewed on our nails and was wondering what had happened, because the initial prospect was that it would be go into orbit, but it was due to come around the Earth in about 91 minutes. And 91 minutes passed and no reception, absolute silence.
And it was a very stressful time there with the Secretary of the Army and von Braun and Van Allen and about maybe half a dozen other people all looking at me because we had no loudspeaker or anything of that sort. I was the only one who knew what was happening. And so I had to sit there and hope that it was going to arrive.
And then I think at about 108 or 9 minutes, Bill Pickering got a telephone message from Earthquake Valley, which was one of the California stations, that they had received a signal. So the whole room full of people just burst into applause, and everyone patting each other on the back and smiling from ear to ear. So it was a great moment, actually, when that first went around.
Finally, America was in space. The media focused on the Explorer 1 achievement as, at last, legitimizing the U.S. as a worthy adversary to confront the communist Sputniks. The public seemed captivated with the propaganda created by this new space race. Data received from the Explorer 3 tape recorder was transcribed, and copies were sent to Iowa and to Dr. Van Allen, who was in Washington at the time. In his hotel room, he plotted the data.
And I began to understand that what was going on here, because we had segments of this orbit when it came down to low altitude, which looked quite normal. Then we had a very rapid change, very rapid increase in counting rate, and then it dropped back to nothing. And then a few minutes later, it came up from nothing to a very high rate and then dropped back to a normal value. And this pattern was repetitive. It seemed to be a systematic pattern as the satellite went around the Earth. And this was the principal clue to unraveling this mystery.
It was immediately obvious. The transition said yes. It went into something that was strong and then went to zero. Therefore, obviously, had encountered intense radiation. And so I immediately took the spare payload for Explorer 3, put it in front of the X-ray machine, and see just how high did I have to take the intensity to drive it to zero. And found that it had to be thousands of times higher than the cosmic ray fluxes in order to do it.
So together, we had Van Allen working on the data in the hotel room, McElwain working on the counter back here, and they came to the conclusion that it probably was a real effect. This is when the famous message from Ernie Ray, space is radioactive, occurred. He simply wrote that, scrawled that on a message and left it on Van Allen's chair, and he saw it then when he came back from Washington the next day.
We have encountered a very great increase in radiation intensity, which is vastly beyond what could be due to cosmic rays alone.
we called it geomagnetically trapped radiation. And I gave an explanation of what my interpretation at a press conference following the scientific session. And one of the reporters stood up and he was trying to visualize what I was saying. And he said, "You mean it encircles the Earth like a belt?" I said, "Yes, that's great. That's what it is. It's like a belt around the Earth." And so that's the way they got the name of radiation belt, from this exchange with this newspaper reporter and myself.
Well, certainly the discovery of the radiation belts was the most important discovery of the International Geophysical Year, because it represented a discovery of some major phenomenon that had a substantial impact both on scientific research and on plans for manned flight later on.
Of course, I'm very proud of having discovered them, and it was a fresh discovery, was not predicted. It was a matter of a great pride to be able to find something new in the world, and totally quite unexpectedly.
How did we learn of these invisible belts in space? How are we exploring this region, and why?
After the launch of Explorer 1, and then subsequently after Explorer 3 and 4 and others, the public interest became very obvious. We were constantly being called for statements, and I became very much caught up in the notoriety that captured the scene.
Yes, it was exciting to see the Time magazine people. It was exciting to see Walter Cronkite come down into the basement.
In late 1958 and early 1959, Van Allen flew instruments on Pioneers 3 and 4. Both were unsuccessful attempts to hit the moon, but their flights provided the Iowa group with essential confirming data. Pioneer 3 documented the existence of a second radiation belt, and Pioneer 4 became the first U.S. spacecraft to orbit the sun.
We participated in NASA flights as soon as NASA got under operation. Of course, we were in a business before NASA existed, so we were in a position to sort of welcome them to the space research field.
In the early 60s, the experienced Iowa group was a clear choice for extending near-Earth satellite research. They built a variety of instruments and satellites for the newly created NASA with obscure names like IMPs, OGOs, and engines.
In this laboratory, we built more satellites, built and flown more satellites for scientific purposes or any other purpose for that matter than the whole European Space Agency, Japan, China, India, the whole rest of the world, except for Russia and the U.S. and the rest of the U.S. in this one laboratory.
I started working here when I was a sophomore in engineering, and I think by the time I was a junior, I was a project engineer on a spacecraft responsible for the whole spacecraft system. And so, in most organizations, they wouldn't let you advance that fast.
And my own role was, I've described off and on as being kind of a scoutmaster of this group. I sort of led defined the objectives and the general intentions, and made all the general arrangements for flights and opportunities. But most of the work was done by the young people in the labs, and they were a great bunch. And we were on a daily basis every day. We were talking about what to do, what was wrong, what would do right, what was a mistake about this, and how did we fix this one, and what's we doing here, and is there any compromise that we could make that would make this work? So it was a give and take every day, and it was a very exciting period.
His work ethics, sort of. By osmosis were filtered down to the rest of us. He was an example of how to get things done and how to work and how to get your nose down to the grindstone. But you got to remember, this guy, he did a tremendous amount of publishing in the science community, and this all had to be balanced against his administrative workload within the department as the department head.
The first era of space exploration clearly was one that was dominated by just the challenge of getting there. Van Allen's contributions were enormous in that era because he invented many of the ways that were needed to actually make scientific measurements in this first era when it was so challenging to even get there.
For the first time in my life, I was really getting important new results almost weekly. And that was a very important development in my professional life because everything we're doing was new, not been done by anyone before. It was first venture into various elements of space research. It was an immensely gratifying period of fresh discovery and new results on subjects which had long been sort of speculated about but not really settled. And we had a grand time, and it was a very maturing experience for me to have something important really going on at the forefront of a subject week by week and month by month. We were producing results which became kind of the standard of the field, actually, in the early developmental period of time.
I think Van Allen was looking at the total picture of the solar system, and he visualized that having got this picture of the radiation belts around the Earth, that there was a lot more space out there to be explored.
In 1962, Mariner 2 was the first ever spacecraft to pass by Venus. Iowa instruments on board determined the sister planet simply had no magnetic field. Mariner 4, launched in 1964, made the very first encounter with Mars, the planet which conjured up so many misconceptions that had long fascinated our popular culture.
And we made a pass by Mars, and my instrument established that it did not have a radiation belt, and that it was essentially not magnetic. Well, from my point of view, that was an answer to what I call the first approximation to the exploration of Mars. And what I call the first order question about Mars in my field of interest is whether it has a magnetic field or not, and the answer was negative. So then I was more interested in going on to Jupiter after that because we had other types of evidence that it was magnetized. So in my field of specialization, Jupiter was far more interesting.
In the early 1970s, Van Allen's instruments flew to the outer planets on Pioneers 10 and 11, again for first ever discoveries. These spacecraft provided spectacular images as they mapped the magnetic fields of the large planets, probed their atmospheres, and investigated their interaction with solar winds.
That program was so successful, had so many firsts. It was the first spacecraft to fly through the asteroid belt, first to go by Jupiter. Pioneer 11 was the first to fly by Saturn, and everything it did was successful. It seemed to me that this was the spacecraft of destiny.
The appropriately named Pioneers were the first to explore the outer planets of our solar system, facing the unknown, as ancient mariners did on uncharted oceans of Earth many centuries ago. They were the fulfillment of our natural curiosity, of our passion to search new frontiers. Dr. Van Allen pursues his studies of planetary magnetospheres with untiring persistence. It is the work he started in 1932 with a magnetic survey of his home county and continued with discovery of the Van Allen radiation belts in 1958 and ventured on to mapping the magnetic mysteries of Jupiter and Saturn. They're both pioneers, the spacecraft and the man, reaching beyond ordinary expectations, partners in search of our origins. The man, the scientist, still communicating with the Pioneer 10 spacecraft as it seeks the interstellar medium, attempting to discover the elusive boundary that defines the very edge of our solar system.
By that we mean the distance from the sun. You know, if you sort of imagine a big sphere around the sun, there's going to be at some distance from the sun which it no longer influences cosmic ray intensity. And that's what we kind of call the heliospheric boundary, right? Where then you pass into the interstellar medium, the medium between the stars. You pass beyond the influence of the sun, and into the interstellar medium. And that's kind of the ultimate objective of my experiment, but I have very grave doubts I'm going to get to that point, to tell you the truth, because I continuously keep an eye out for that and analyze my data with respect to that objective.
It encountered Jupiter in 1973. Ever since then, it's been getting farther and farther out, and it's still working. And I'm gratified to know that the Iowa instrument is still being operated, and that Van Allen is still looking at those data and still looking for the heliopause, because I hope he succeeds. I hope he achieves that destiny.
This little spacecraft is out at the extreme far edge of our local universe, sending us information back. And in many ways it is like Professor Van Allen. He comes in every day and he looks at his Pioneer data and he works at it and he analyzes it, puts it together with data from other experiments, and they're both still useful. They're giving us things much beyond what we ever expected.
I've never thought of myself as particularly brilliant, anything of that sort. I've run across so many brilliant people in my life who run circles around me on, sheer brilliance and understanding. But I don't run across very many that have the same quality of persistence and perseverance that I do. And when I really am onto something, I'm going to still be on it 10 years later if that's what it takes to get the answer. That's the kind of thing that keeps driving me onwards, is that there's always some other thing you really should know if you want to get the whole picture.
There's two principal parts of his legacy, all right? One is doing a fantastic job on his science, which yielded extremely exciting results. And two is the human legacy, is the training of a whole corps, all right, of space scientists.
Probably one of the biggest things he sort of taught me, or I sort of realized working with the man over the number of years, is that the way you stay in the business is you got to keep getting rides. And if you can't fly hardware, you can't do science. And if you can't do science, you're going to sort of fall in the background of this whole business.
The love of data, the love of investigating, the importance of honesty, of personal integrity, of working with others, of helping others. These are all things that I have seen in Dr. Van Allen. I've learned from him, and others have learned from him, that in addition to being a wonderful scientist, a good scientist, an innovative scientist, an explorer, is that he is a kind human being.
The Jim Van Allen legacy to science is, in many ways, a quintessential scientific approach of simple, elegant, economical experiments which address the key scientific issue, and then very insightful analysis of the data you have to understand nature in a new and fundamental way.
That's what I'm doing at the present time. I really work quite hard. I don't get exhausted particularly, but I work up to my full capabilities every day. And that's sort of characteristic of my whole life, is I really believe in what I'm doing, and I love to do it, and I'm going to keep right on doing it as long as I'm capable.
The preceding program was produced by the University of Iowa in association with the Big Ten Network.